Okay. Hi, Jasmina. Hi, Jasmina. How you doing?
Hi, I'm good. How are you?
Peachy keen, wonderful. Is that stuff coming to you a little easier?
Yeah, definitely. Now that
Okay.
I've gone over it and stuff.
It's new stuff, so it's not surprising that it's taking a while to sink in. So we're going to go through a little bit more of it tonight. Okay.
All right, sounds good.
Yeah. Sounds like you're tired and you just want to get out of here.
Yeah,
Half an
it's been a
hour.
long day.
Half an hour, no longer. Dylan, you doing okay?
Yep. How about you?
Just peachy keen, wonderful. Just found out today, PowerPoint I was working on for tomorrow just went into the oblivion, so I'm real happy about that.
Of course, the day before.
Yeah, there you go. And speaking of which, I don't understand where that went. Okay. Fine is kind. So actually, I hate when I do things tomorrow. I can't blame anybody. You know, it's almost better when you can blame somebody. And who knows, it may be down to just the two of us, or I'm sorry, the three of us.
Is this PowerPoint already up on my courses?
Should be.
All right, thank you.
I could figure that out momentarily. Okay, you're not seeing anything on the screen right now, right?
We see the PowerPoint.
Okay, good. It's not a big deal. I'm just into the course, and you just asked me a question. I was going to go try and figure it out.
Yeah, it's open. I looked.
Oh, it is? Fine as kind. Great.
Yep.
All right, so I got two of you in here, right? Ian decided to come in. Good. Okay, Ian, you're good? You in here, Ian?
Yes.
Okay. I don't know that Jackson should be here. Jackson generally eats and then joins the place a little bit late. I'll give it one more minute, guys. Any questions on what we went over today in lecture? Anything?
No. Just the speed of light, but we'll get to that on Thursday anyways.
Speed of light is, you want to know what it is?
Oh, no, I was just confusing when you were going over it in lecture. But no, it's all good.
Basically, the only equation I've gotten so far is the speed of light is equal to the frequency times the wavelength.
Right.
Okay. Speed of light
No,
is.
what I was confused with was the first problem you showed there at the end, and it was
I gave you the wavelength and I asked you the frequency.
Yeah, and we had to convert it to meters, and it was in scientific notation.
Yeah, because normally speaking, when you're dealing with wavelengths in the UV range, they're given in nanometers.
Okay.
Okay, and it's about 200 to 600 nanometers. Okay.
Okay.
So because the speed of light is in meters per second, you have to convert the nanometers to meters in order to divide it into the meters per second.
Okay.
Make sense?
Yes.
Guys, just talking a little bit of lecture there, all right? Everybody doing okay? A great resounding nothing. All right. We're dealing with calorimetry problems tonight. That's what the lab was going to be. The first one, I'm just literally speaking the experiments are almost self-explanatory. There are 3 experiments we're doing. The first one involves taking a piece of metal, and we're putting that piece of metal into a boiling water. Okay. Specifically speaking, we're trying to keep the metal dry, so we're sacrificing a little bit of the heat in order to keep the metal dry. So what you do is you put the metal in a test tube, and then you put the test tube into boiling water, and you let the metal in there for about 15-20 minutes so that the metal gets up to boiling temperature. Okay? So while this is going on, while this is heating up, you're getting your calorimeter ready. Now, you have to weigh the calorimeter. Then once you weigh the calorimeter, you put enough water into the calorimeter to barely cover the metal that's in there. Then you put the calorimeter with water back on the scale. Calorimeter and water minus the weight of the calorimeter, you have the weight of the water. Okay? Then while this stuff is boiling up, you put your thermometer into the calorimeter and you get the initial temperature of the water. Okay? Then, as quickly as you can, after the metal's been boiling for about 20 minutes, you quickly take it from the boiling bath and you plunge it into the calorimeter. Close the calorimeter off, swirl it around, and you wait till the temperature gets to its highest level. That's the whole experiment. The thing that takes the most time in this experiment is the boiling of the water. So we have 2 equations that we're dealing with. We have the Q is equal to ms times delta T, and we have the Q of the system is equal to negative Q of the surroundings. In this case, the system is going to be the metal that we're putting in there. We've heated the metal up. That metal is going to lose temperature as it's put in the water. So that is the system. On the other hand, when the metal gets put in there, the temperature of the water is going to go up. So the Q of the water is the same, but opposite in sign to the Q of the system. Are we good so far, guys?
Yep.
Yes, sir.
All right. So we weighed the calorimeter. It weighed that many grams. The water and the calorimeter weighed that much. What mass of calorimeter is 2.5609. Calorimeter in water is 46.1603. The mass of the tube in the metal is 91.5872. Mass of the tube is 30.66005. The initial temperature of the water was 24. Initial temperature of the metal, the temperature of the water it was boiling at, was 98.4. Our final temperature of water is 29 degrees Celsius. So we have 2 ways we can set this equation up. Since the Q of the metal is equal to, negative Q of the metal is equal to Q of the water, I can take, this whole thing up at the top. I could take negative, the mass of the metal, times the specific heat of the metal, times the change in the temperature of the metal, is equal to positive, the mass of the water. I don't know what I was thinking. Mass of the water times the specific heat of the water times the delta T of the water. I can do it all in this big one long equation. I prefer to use simple steps. Okay? I do the Q of the water is equal to mass times the specific heat times the change in temperature. We look back. I get the mass of the water by taking the 46 grams and subtracting the 2.5 grams from it. I do that out and I have 43.5994 grams of the water. Specific heat of water is 4.184. And my change in temperature, my final temperature of the water was 29, my initial was 24. So all I'm doing is plugging those numbers in. I have my mass of water times my specific heat of water times the change in temperature. I do that math out, I get 912 joules, a positive 912 joules. I also know the Q of water is equal to negative the Q of the metal. So if the Q of the water is 912, the Q of the metal has to be negative 9.9, negative 912. Now I'm going to plug this into the metals calorimetry equation. I've got my heat of my metal, 29.0 minus 98.4. So I got a big number here of minus 69.4. I've got my test tube and metal minus my test tube. I have my mass of my metal. So I'm going in, I'm plugging my mass of my metal times my specific heat times my change in temperature is equal to the Q of the metal. I divide the Q of the metal by the mass times the temperature. I get the specific heat. I take my specific heat and divide it. I take my specific heat and I divide it into 25. And that is the formula you get for getting the atomic weight of a particular substance. Okay,
Where was
do I
the
have,
25?
I'm sorry, why is it
Where was the
25?
Yeah.
Because I have not, there is no scientific reason for it. You just had some people that were math nerds. And what they did was they kept on taking the specific heat and dividing it into numbers. And somehow they came up with the fact that 25, if you divide the specific heat into the number 25, you get the weight. There's no rhyme or reason for it. It just
All right.
happened that some math people got together and figured it out. If you can find a reason, I'll give you 100 points on one of your labs.
I will be researching.
Okay, go for it. Okay, are we good with that? That's the entire first experiment.
Yes, sir.
All right, are we understanding the calorimetry aspect of this?
Yeah, could you go back one slide though, if you don't mind? Thank you.
Okay. Are we good with this, guys? All right. Now, the second experiment is going to be just a tad different. All right. Just a tad different in the fact that we're not comparing our heats with one another. We're not really comparing the heats with one another. In other words, we're not trying to get a specific heat or a final temperature or initial temperature or anything like that. What we're doing with the second one is we're trying to get an enthalpy per gram of sample that gets dissolved. So the second experiment takes a known weight of my salt. Okay. I have a beaker. I weigh the beaker. I put some salt in it. I weigh the beaker and salt. I can subtract the two. I get the weight of the beaker. Same thing with the calorimeter. I still know the mass of my calorimeter. I add some water in there. I put the calorimeter and water on the scale. I get that weight. Then what I do is I take my entire mass of salt, put it into the water, close the lid, I'm stirring it, and I'm looking at the temperature. Sorry, there was one more step. I needed to get the initial temperature of the water. So I'm stirring it around and I'm looking at the temperature to get the highest or lowest temperature that happens. In this case, when I put the salt in there, my temperature went down. So I've got all the information I need to do this. And remember, my final result is going to be joules per gram. So let me riddle me this, Batman. What am I getting the temperature of? What am I taking the temperature of?
The
The
metal?
water.
There's no metal here, guys.
The water.
I'm taking the temperature of the water. So in order to get the heat, what mass am I going to use? Am I going to use the mass of the water or am I going to use the mass of the salt?
The mass of the
Mass of
salt.
water.
You cheated. Yes, you're correct. By the time you add the salt in the water, it will be salt water. But the media we are determining the change in temperature of is the water. So if that's the media we're determining the change in temperature of, we're going to need the mass of the water. Does everybody understand why we're using the mass of the water in that step and not the mass of the salt? Because we're not determining the temperature difference of the salt. We're determining the temperature difference of the water. So in that step, we're using the mass of the water. Again, the Q of the water is going to be the mass of my water times my specific heat of water times my change in temperature. My mass was the calorimeter in water minus the weight of the calorimeter. That gives me 50.3990 grams of water. My final temperature was 16.3. My initial temperature was 24.1. So note, guys, I have a negative change in the temperature of the water. I multiply my mass of water times my specific heat, which should be that, times my change in temperature of water. I get the Q of my water as being minus 1600 joules. The water is my surroundings, guys. What my system is the salt getting dissolved by the water. So my salt getting dissolved by the water is going to be equal to negative the Q of the water. Since my Q of water was a negative 1600 joules, my Q of dissolution is going to be a positive 1600 joules. Then the last step, guys, if I want joules per gram, all I got to do is the amount of energy I got by dissolving the salt was a positive 1600 joules. All I got to do is find the mass of my salt and divide my 1600 joules by that many grams, and that ends up being 160 joules per gram. Questions on this, guys? The main thing about a problem like this is you have to realize what you are taking the temperature of and therefore what you're trying to determine the Q of. If you're trying to determine the Q of the water, then you need the mass of the water.
And the specific heat of the water, it's given, that's not something that we find.
Correct.
Okay.
4.184 joules per gram centigrade. Or if you want to solve for calories, it's 1 calorie per gram degree centigrade.
Thank you.
Any other questions here, guys? Dear God, please. Ian, are you here listening? Ian.
Yes, but I have a work phone call quick.
Okay. Dear God, ladies and gentlemen, 99% of these problems, you will be limited in significant figures by the temperature. Look, my weight is out to 6 sig figs. My temperature is only 2. Even my constant is 4. So look at the temperature, please, and look at the temperature and use that to determine how many significant figures your final answer should have. Okay? Questions about the second one?
No, sorry about that though.
No, is that you, Ian? Is that you back,
Yeah.
Ian? Okay,
Yeah.
Ian,
Yes.
to reiterate, and I
Uh-huh.
know you have a problem with sig figs. When you are
Uh-huh.
doing calorimetry problems, look at the
Right.
number of significant figures of your temperature difference.
Okay.
99% of the time, that will indicate how many significant figures your final answer should have. Okay?
Okay.
All right. Last thing. We're dealing with the enthalpy in kilojoules per mole of a reaction. Acid-base reactions are very, very exothermic. If we add sodium hydroxide with HCl, there is a 1-to-1 stoichiometry. And if you look at the amounts of both materials, I got 50 milliliters of 2 molar HCl and 50 milliliters of 2 molar NaOH. So I have 0.5 moles of each. They limit each other. Remember, when we are dealing with enthalpy reactions, where we know what the heat is and we want to know the heat per mole, we have to know how many moles we have, because we want the enthalpy per 1 mole. All right. The other thing that's strange here is, you notice we're only going to be using the 0.500 from either the NaOH or the HCl. It doesn't matter which one you use. On the other hand, when I'm going to figure out the Q, I need the total weight. To get the total weight, I'm going to add the 50 milliliters of the NaOH and the 50 milliliters of the HCl. That's going to give me 100 milliliters. I'm going to multiply that by 1.02, which is the density they give you for the salt solution. So I multiply that out and I get 102 grams as the weight of my solution. When I do this, I take my initial temperature of my NaOH, I take my initial temperature of my HCl. Now, to get the initial temperature of my solution, I'm just going to average those two, so that my average is 23.3. I mix 50 milliliters of my NaOH in with 50 milliliters of my HCl, and the temperature goes up to 37.4 centigrade. So from the previous slide, I know that my weight of my salt solution is 102 grams. My weight, my constant is 4.184 joules per gram centigrade, and my temperature difference is 37.4 minus 23.3. So all told, I multiply these things together, I get 6,062 joules. But my Q of water is negative Q of my reaction. So my Q of reaction is going to be a negative 6062 joules. I need to turn that into kilojoules because the question asked me for kilojoules per mole. So I multiply this by 1 kilojoule over 1,000 joules. I get a negative 6.062 kilojoules. To determine the moles, what I need to do then is I need to divide the kilojoules by my moles. And this, I think, is a little, yeah. 50 times, that answer was wrong. So my moles of sodium hydroxide and HCl is 0.100 moles. I take my kilojoules, divide it by 0.1, and my final answer is going to be 61 kilojoules per mole. I waited till the very end because I knew my final answer was going to have 2 sig figs. I just waited till the very end to make that final determination. All right, those are the three experiments you're doing. Anybody have any questions about any of the 3 of them?
Can you go to the first slide on this experiment?
This
No,
one?
oh no, I meant for experiment 3.
Oh. That one?
Yes, thank you.
Guys, that's all I got for this week. If
How
don't
did you
have-
find?
I'm sorry,
Sorry.
please.
How'd you find the number of moles? The 0.100.
Okay. 50 milliliters times 1 liter over 1,000 milliliters gives me
Oh.
0.05000 liters times 2 molar gives me 0.100 moles.
Okay. That makes sense.
Anything else out there, guys? Well, in that case, anybody have any questions about the lecture or something another lecture teacher may have said? I'm hearing crickets, guys, and I'm hungry. Okay. You all take care, and I will see some of you on Thursday. The rest of you I will see next Tuesday night then, okay?
Okay. Have a good night.
You
Have a good night.
night.
Good night, sir.